I think you have perhaps hopefully seen the material was shared on a website. If not, you can also scan this code and access the material. So we will have the first part, which is a presentation, and then we have a hands-on part, and the material to follow the hands-on part can be accessed here. There are also installation instructions. Yeah. But we will also do this as a demo, so if perhaps you have not installed one of the tools or so you can also follow it and see how it is done. Yeah. So that's the rough agenda. So first we have this presentation, which gives more the motivation and background of FMI and explains the idea, the technical idea behind it. We will also have a short outlook on FMI 3 because that's the future. Then we will have a hands-on part where we first start with working with one FMU. And then we will look at multiple FMUs. And then in the closing session we will have an outlook what could be done with FMI-based simulation.
Just sorry to interrupt. We need to make sure that we have a recording of the room being silent when we ask you that you consent to being recorded. So everybody consents to being recorded. Good. There are noddings for the record. People are nodding. So we can continue.
Yeah.
Yeah.
And I think we are not that big a group, so I think we can do this really interactively. So if you have questions for understanding, you can ask immediately so that you can follow. And after each part, we will also have the possibility to ask questions. But I think if you have questions, just ask. Then let's get started. First with this introduction to FMI. So the motivation behind FMI was to have a tool-independent standard to exchange and co-simulate models. And the idea is to provide a model in a containerized form that can be reused and deployed easily on different targets. And by this, one decouples also the knowledge between producer and users of this model. And also different expertise comes into play. There are specialized modeling engineers, for example, and also software programmers and users of the models, and one can decouple this. So it's about massive reuse of models. Another aspect is IP protection. So if you have a modeling tool, often it's white box, and one can look into the model, see the details, but in some use cases you do not want this. Perhaps if you share it model with a supplier, then you want only to exchange the model so that you can simulate it, but not expose the details. And that was the reason why in 2008 there started a big European funded project, Modelica, initiated amongst others by Daimler, to create such a model interface. And the idea behind this you can see in this picture. So Daimler as an OEM, they build cars from many suppliers, and in the same way they also want to collect models of the different subsystems and components and generate a big overall simulation model from this. And this is also where the name comes from, functional mockup interface. So for CAD data, they do the same. So they collect the CAD data and create one big CAD model. And here we do this on a functional simulation model. And instead of digital mockup, as it is called for CAD, we call it functional mockup. That's where the name functional mockup interface comes from. Then at the end of this Modelica project, FMI 1.0 was released. in 2011, and shortly afterwards, the FMI project found its home in the Modelica Association, and then FMI2 was released, which was then also stable for a long time. And this is also what is, let's say, currently the most often used version. And we will also use FMI2 in this tutorial, because you will find FMI2 support in almost any simulation tool. But later we will give an outlook on FMI3, which was released last year, and has many new interesting features for new use cases. So that's why we will give an outlook. We want to explain the versioning scheme of FMI. So, for example, for FMI 2.0.4, FMI 2, that's the major version. That's where really new features come in, and this is non-backwards or forward compatible. So you need really FMI 2 implementations or FMI 3 implementations. So this is for the major changes. The next digit is for minor releases. So so in fact we never released a minor release until now. So there was no 2.1. This was discussed, but we then went for 3.0. But the idea is here that this is backwards compatible in the sense that a 3.0 FMU will also be a valid 3.1 FMU, while the 3.1 can have new features, but you have this compatibility. That's minor releases, and we will work on a 3.1. We already work on this, so that's about minor releases. And then there's the last digit. This is about bug fixes and maintenance releases. So here we do not introduce new features. This is for clarifications and bug fixes. And this is backwards and forward compatible because more or less, for example, for a bug fix, you have to fix it, but perhaps if this does not affect you, you can still exchange a 2.0.1 FMU with a 2.0.4 importer. So this is for minor things. One must say in FMI2, we backported some of the features of FMI3 that were not of the core standard, even to this 2.0.4, but this is more an optional extension. And but now for FMI3, we have this clear semantic versioning scheme. So interrupt me if you have any questions. Okay, so now how does it work? So typically we have at least two tools involved. The exporting tool, that's where the model is developed. And then we export it according to the FMI standard in the form of a so-called functional mockup unit. So the unit is the thing that is exchanged between the exporting tool and the importing tool. And the interface, this is about this FMI standard, which explains in which form this FMU has to be exported. And then the importing tool can take it independently from where it was exported, because it's agnostic to where it comes from. It only looks at the interface. And then you can, in the importing tool, you can simulate it or combine it with other models, co-simulate it, whatever. That's the basic idea. And also, to explain, let's say, where FMI at least originally comes from, we shortly talk about what kind of models can be in there. So originally, people thought about ordinary differential equations, perhaps also combined with some discrete equations with events. And this is also the reason why, for example, I think this is in the Modelica association, because this is also what you can build with Modelica very nicely. And then the tool vendors, they thought about an exchange format, and this is, let's say, the connection to originally to Modelica. What's important, there is a notion of time. So typically you don't have a real thing inside an FMU that is only triggered once, but there is some evolvement over time. It could also be more generally, it could be about, it could also be an angle or so, but then you call it independent variable. But in almost all cases, it's time that evolves. And beyond that, you can, let's say, you don't need differential equations inside. And you can also use it for, more and more it's used also for more discrete systems, for example, virtual ECUs, where you have embedded software inside it. And that was also one of the drivers towards extending it for FMI3, where many new features in this direction were included. And also today you can, it doesn't have to be physics-based equations, let's say, that are modeled here. It can also be machine learning models or so. And also FMI3 has features to support this, for example, by getting partial derivatives that can be used for the training. Let's shortly talk about co-simulation, because we will later talk about one kind of FMUs that's called co-simulation FMUs. So here the main idea is that you want to simulate an overall system, and you have split it, or the origin of these submodels, they often come from different tools, exporting tools, and you want to couple them to simulate an overall behavior. But this is closely coupled, and you have to simulate it simultaneously, but the important thing is here that you don't expect it to be exact in the sense that it would give exactly the same behavior as if you would model it in one tool, but you can live with certain kind of error, which you have to control by, and you can influence this by selecting a suitable orchestration algorithm, we call it co-simulation algorithm, and also design a certain communication pattern, for example, selecting a suitable communication step between these submodels. Yeah, that's co-simulation, and we have one special kind of FMUs that are designed for this kind of co-simulation. Now, we said that the FMI standard defines the interface, and this is reflected in the C API. So we have API so that from the outside, for example, the importing tool can, for example, set a variable or get a value or trigger a computation step, and for that we have an API defined. We have an interface description in an XML file where you define, for example, that this model has certain inputs, certain outputs, certain parameters. And then we have this container format where we technically use zip. So you get a zip file which you can also open with any zip tool. And also there a certain structure is defined what files go into this zip file. One important takeaway is that the FMI interface defines only the interface to one FMU. even though normally you couple it with something, you simulate multiple FMUs, you co-simulate them, but the algorithms about the co-simulation, they are not defined by the FMI standard. There is freedom, so you can select the suitable algorithm. The only thing the FMI interface defines is the interface. Now, if we look into this FMU zip file, we have this model description, and then at least one model representation. It can be in binary form, so for example a DLL for Windows, or an SO file for Linux. It can be multiple binaries for multiple platforms, or it can be source code, C code for example, that allows you to recompile or recreate a binary for a new target, which is also a nice deployment mechanism to some new target. And there are additional folders for resources, could be, for example, certain data that the model uses, for documentation, also an icon. Such things can be put into this zip file. Are there any questions until now?
Maybe a short question. So the notion of time, it has to be discrete or continuous?
Can be both. So this is a property of the variables. If this is a continuous time variable or a discrete time variable, and the FMU can contain both. So. And from the communication, in the next slide we will see this, the different FMU kinds, so this model exchange and code simulation. So at least the communication structure in FMI2, this is really discrete because you have communication points where data is exchanged. In between there can be something continuous, but at least for these co-simulation FMUs, the communication structure is at least discrete, even for continuous variables. And for model exchange, which I will explain now, there you have the notion that you have the model inside the FMU, and the solver for this differential equation, this is outside. This is coming from the importing tool. And here you have, let's say, a very, very tight coupling, and this is often something very continuous because an ODE solver, this typically also has a variable step solver, so this is, here is more this continuous behavior, and here internally it can be both, at least from the communication structure. It's in FMI2 it's discrete. So model exchange FMU, as I explained here, the model is, or the model equations are inside the FMU, and the solution algorithm for these differential equations, this is in the importing tool. And you can imagine that this must fit together. So for example, if you have very stiff equations coming from a hydraulic system or thermodynamic systems, you need here a suitable solver. And that might be a reason why in industry most often co-simulation FMUs are used, because here you can couple them together. So you have, let's say, always a suitable solver for the model. On the other hand, there are important use cases for this model exchange FMU. So, for example, if you want tight integration of a model with the solver of an importing tool, then this is the way to go. So, for example, we are here at the Modelica conference. There are some tools who do not have a native Modelica compiler, but who they have licensed a Modelica compiler, and they, under the hood, create an FMU and import this and expose in this way the Modelica processed equations to their solver. That's an important use case for model exchange. Co-simulation, as I mentioned, is most often used in industry at least. We mentioned that here model and solver are tightly coupled together, but also it's important to see that then you have a freedom in this co-simulation algorithm. And also there can be lots of things can go wrong here, but you can select suitable co-simulation algorithms and suitable communication time steps. And we will later see this in the third part when we talk about simulation of multiple FMUs. Sagst du?
Yeah, maybe you should mention like model exchange works only, you can only expose ODEs, but
Yeah.
it doesn't work for DAEs and all kinds of other equation systems. So that's not obvious from the slides. I
Yeah,
think.
thank you.
To us it is.
Okay, here for this co-simulation interface, the important thing is this communication time steps. This is where information between the different FMUs is exchanged, and internally there can be a different time step. You can have a variable time step internally and have, for example, a fixed larger communication time step. And then the typical calling sequence according to the FMI standard is that you set input values, then you make a do step, so you advance time, and internally the propagation of time is calculated, and then you get outputs. You can have a look at examples. We provided the material, so I think you can look after this on your own, or perhaps in the, don't know if in the second part we can have a look at this. And yeah, once again we tell here that the master, or the co-simulation algorithm, previously it was called master algorithm, which is not such a good name. So this, you have a freedom, for example, which time steps to take if you want to extrapolate, yeah. So there you have a freedom. So this is not part of the FMI standard. For model exchange, I think we explained these things already. There the idea is you have more or less the equations and expose them to the solver of the importing tool. And also here, it's not defined by the FMI standard which solver the importing tool uses. It's up to the users to select a suitable one. And also, if you have multiple FMUs, you can, let's say, decouple them from this numerical solver co-simulation algorithm. The communication is via this standardized interface, and this solver or co-simulation algorithm is not defined by the standard, but by the importing tool. Okay, this model description, it contains the static information about the model. So one important thing is which kind of this FMU interfaces is supported by the FMU. So we saw on the last page model exchange and co-simulation. An FMU can also contain both. Then the importing tool selects which interface it selects. In FMI3, we will see a third kind, the scheduled execution. The model description XML explains the model variables so that the importing tool can access them. And also certain information about the model structure. So for example, to detect algebraic loops, you need some information how the inputs and outputs of a model are connected. And yeah, then you can have a look at this XML file, but typically an end user doesn't do it. So this is something that happens in the background. More or less normally only the exporting tool and the importing tool, they touch this XML If you want to look very deeply into it, you can do it, but normally you don't see this. And there can also be additional information, so-called capability flags and attributes. So there are some optional things in the FMI standard or some additional information. So for example, an attribute needs execution tool. There are certain kinds of FMUs that are not standalone. So this, more or less from the idea from the FMI standard, you want a portable model that is tool independent, you can ship it to anyone. But there are use cases where you get an FMU, but in order to execute it, you need a certain installed program or certain libraries. And in this case, this attribute needs execution tool is there in the XML file, and then it looks like this. So when you import an FMU into your importing tool, this is more or less only a wrapper. It doesn't do the real calculations, but it communicates, for example, with some installed simulation tool, which contains the models and the solvers. And here, this wrapper FMU more or less only does the communication to the importing tool. For example, for multi-body simulation, typically the tools do it this way. Are there any questions?
Hi, Christian. Yes, Kahraman from Codis. I have a question regarding the licensing. If Solver is integrating or importing different functional mock-up units from different suppliers, the any standard, I'm wondering if the licensing, how will be agreed for the licensing? Or is it out of scope of this standard?
It's out of scope of the standard, so it's up to the tool vendors that export to define this. And the FMI standard is more about the technical interface, and you can make agreements and licensing. We will also have a slide on this. It's beyond the technical interface.
Okay.
So it's a good practice to put information about this in the documentation. So there's documentation folder inside the FMU, so that if a user gets it, also importing tools should provide a possibility to display the documentation. Then you can write, okay, this FMU requires a certain license or so, but this is outside of the scope of the FMI interface standard.
All right, thank you.
Regarding tool support, there is on the FMI website, there is a tools list that grows, I would say linearly, so more or less every week currently there come one or two tools, and currently it's supported by more than 180 tools. One can say it's more or less the de facto industry standard for tool independent model exchange. And it's supported by almost all simulation tools on the system level. So you have typical, for exporting tools, you have the typical modeling and simulation tools. So there are also tools that are more into the, for example, embedded software creation. They also provide FMI interface. And then also you can wrap existing code, like for example for ECUs, you can also wrap it into functional mockup units. For the importing tools, you have typically all these modeling and simulation tools that export. They can also import FMUs, but you have also specialized co-simulation or integration platforms, and also many programming languages that support FMI. When we created FMI 1 and 2, in the beginning there were also problems that, let's say, importing tools had problems simulating or importing FMUs, and at that time we created a so-called cross-check. So that exporting tools provided FMUs and reference solutions, and the importing tools could simulate them and compare the results. This was very successful, but it was so successful that the effort exploded. And that's why currently we are on the way of implementing a new thing. So in this tool list on the FMI webpage, you will find FMUs or tools that have a golden star. And these tools, they provide what we call compatibility information. So the tool vendors themselves, they report with which tools they have tested. So for example, importing tool can say, okay, here I provide, I have tested, an importing tool can say, I have tested FMUs from those 5 tool vendors, and an exporting tool can also provide example FMUs and also say with which importing tools they were tested. Here, this is about this licensing, that what you asked. So this is not part of the technical standard.
Okay.
And there's not only licensing mechanisms like FlexLM or FlexNet request or so. It can also be other legal obligations that are not part of the FMI standard, but from some tools, they say, for example, you can ship an FMU that you can create from my tool to one party, but then it may not be further distributed or so. Such things can be obligations from other license conditions that you agree on. Are there any further questions now? No? Then I would give a please.
Quick question on the previous slide. So you mentioned that about the compatibility issue.
Yeah.
So could it be that there are 2 FMUs that are not compatible with each other in the correct FMI environment?
Yeah, if everything is corrected right, then it shouldn't happen. But yeah, so it's programmed by humans typically, and they make mistakes. So we have seen lots of corrupt FMUs. And there are ways to validate them. I think also on the FMI webpage you will find a tab validation. So we offer different checking tools. As I think Thorsten will show some of them in the second part. So this is for validating FMUs that you get from somewhere. But typically there you mainly detect faults in the XML. But there also lots of faults have been made in the past, but there are very good checkers where you can now say, okay, this FMU is corrupt. And yeah.
It also depends on what you mean compatible. You mean, can you get a result from other connection, or can you trust the result?
Well, I mean, in my mind, so when you export a model, let's say at the FMU level, then when you connect various FMUs, you lose the causal. Of course, that is a huge advantage. That's normal, of course, because then you go to the sequential coding in a sense. Okay?
Mm-hmm.
And so incompatibility can come because you may have an array output and then there is an expected scalar input. But this is not what I mean. This is natural.
Yeah.
This means that they didn't talk to each other. So okay. But I mean not more like deep incompatibility. So if we have like an FMU that is corrupted by its nature, regardless of how I'm going to try, because I may be fighting to make it compatible, but it could be a deeper issue behind this that I'm not aware of. That.
So typical examples are in the XML. These are things that you can really validate and say this is right or this is wrong. What is more complicated when you, for example, connect 10 FMUs and try to do a co-simulation and something goes wrong, then it can have lots of different reasons. And this is not about black and white, so then you have to dig into the system, look into the frequency behavior of the different FMUs and so on. So there might be, so FMI does not solve all of the numerical simulation problems of the world, but there are, what we here more want to exclude is really the obvious faults. So for example, if you're the XML, you can decide is this right or is this wrong. And in the past, most problems came from that, but now we can concentrate on the more real numerical problems, and they don't go away with FMI.
They just are brought more to the surface because now more people are connecting these things.
Put another way, like even with the most robust FMU, there's infinitely many possibilities to break a simulation, if that was your question, yes. But we're trying to avoid as many of them as possible, especially the common ones.
Yes, I have another question. So Daniel Janning, Danfoss Drives, And you said that FMI is the industry standard for sharing models between different tools, and that was also my impression until now, but some weeks ago I talked to a colleague in the US, and he was in strong doubts that the FMI is spreading around in their industries. Do you have a feeling how this is used internationally and not only on the European market?
So I think we have broad support also internationally. Also now some very big US companies who are not until now part of the FMI project. So let's give, for example, the example MathWorks. If you look at the latest release, they have broad FMI3 support. So more or less they are, so I would say we are not limited here to Europe. It perhaps depends on the industry. So there are industries that have their, let's say, industry-specific own standards. So, but we are in talks, for example, with the aerospace industry, where it's partially used, but they have their own standards that are not used outside their industries.
Which format, which standard was he using?
No, we were talking about the FMI, and they were not using any standard by now.
Okay.
But,
So we are aware that you can also use native formats. So you can use formats of one
exchange, for example,
simulation tool or so. But what I said, this is the, let's say, industry standard, de facto industry standard for tool independent model exchange.
Yep.
And I think there perhaps in the three-dimensional simulations there might be other things, but here on the system simulation level, I think there is nothing more commonly used.
Yeah. Okay, so you have not heard anything that there's a big spread in the usage between different areas on the world?
Well, one can say, let's say, from the beginning, FMI, they had many support from the automotive industry. I think there it's also most broadly used, but also now in the buildings industry, it's commonly used from the aerospace. They have classically, I think, there all the engineering is standardized very much, and they have very high security and safety requirements. So from their history, they at an earlier stage defined their own standards, but they did not spread beyond their industry.
Mm-hmm. Thanks.
To make an extension, in the moment there's a little change if you are using causal modeling. It's more how you model your systems. And here is sometimes now a little changing to acausal modeling. And therefore we need the link between Modelica and FMUs. And 5 years ago, people were trying to transform every model to causal modeling.
Mm.
So FMI is the second best solution, but the only one that works. Okay, so I think we have to a little bit look at the time. So with FMI3, I only want to very broadly sketch this. So FMI, so okay, we have FMI was very successful, but there are new use cases. I already mentioned some of them. Virtual ECUs, for example, advanced co-simulation that goes beyond this discrete communication at fixed time steps, events in systems, and also new application fields like AI models. And also, in some use cases, one saw the demand for a third kind of FMU type, scheduled execution. This is more for discrete simulation, for example, ECU software, where you can externalize a scheduler. And so these are the main ingredients of the FMI3, the new features. It can do everything that FMI2 can, plus event mode in co-simulation. So for example, that you detect when a ball hits the floor, you then simulate until this point, do the event handling, and then simulate further. You can exchange information in co-simulation even between the communication time steps to have, for example, better extrapolation behavior. You can have model discrete behavior in the form of clocks and synchronize events. We have new variable types that are used, for example, for virtual ECUs. Array variables, so in FMI2 we have only scalar variables, and only by a naming convention you can, for example, somehow mimic arrays, but it's not efficient. And we have here the array variables. We have new kind of input and output grouping in form of terminals, that it looks like an causal multi-signal port in Modelica. Under the hood it's still causal. Also better icon representation, the scheduled execution that I mentioned, and also a preparation for extension mechanisms in form of layered standards. We will give a talk on this on Wednesday. So this is for new use cases that go beyond the core application of FMI, where you can define extensions to the FMI standard. So there are lots of resources, especially on the web page, tool list, also with validation tools, list of publications. There are the reference FMUs. I think Torsten will also show and mention them. And also, if you have any questions regarding usage of FMI, we recommend to use Stack Overflow. And there's also a LinkedIn group. This is more about sharing information, for example, use cases or tools. And before we go to the hands-on part, I would like to explain the example that we will use there. So it's a simple Modelica model. So we are at the Modelica conference. Let's show it with the Modelica model. So you have here an electrical machine, a simple driveline with a gear and a mass, and a PI controller. And as the inputs, we have here, so this PI controller, this wants to reach a certain angular velocity of this electrical machine. And so that we have some example that we can look at in the different demonstrations. We have here this behavior that we want to see here. So at time 0.1, we have a step in the desired angular velocity from 0 to 10 radians per second. And at time 0.5, we have a step in the load torque from, I don't remember. There's a step in the load torque.
Speed bump.
Yeah. Okay. And so one can simulate this model and get this result here for the angular velocity. So here's the jump in the desired angular velocity. It has some internal dynamics, so you have a little overshoot here. And at this time 0.5, you have a little bump here in the velocity until it is controlled out by the controller. And we can now export this either as one FMU, or we can split this into 3 parts, where we say, okay, this is the driveline, this is the PI controller, and here these are the stimuli, and you can export this as 3 FMUs, so that we have an example then also to couple multiple FMUs. Okay, do you have any questions? Yeah?
Does the structure of the system dictate on how can it be split?
In general, you want to do it along compatible interfaces. If for example, you were splitting that inertia into 2 parts, then you would really have to think about how we're going to couple this in a physically meaningful way. We can discuss more later if you wish, but I wouldn't say this is beginners.
That's the important point.
Part 3.
It's a scale.
Often, in reality, models are split according to organizational structure of the companies that are involved, which is not the best idea. But yeah, one should look at the physics, and for example, there is sometimes some natural decoupling of systems, which is a good point to cut, but reality often looks other, and then you can try to repair it by some advanced co-simulation schemes, but it's always better to do it meaningfully.
I also have a question. Once we export the FMU from the one certain software, is it also
We'll show that in part 2.
Yeah.
Okay.
So you can, for example, change parameters.
Or some connections within the model.
So if this would be switches that you expose, so for example, in form of parameters, you could do that. But typically, the structure is fixed. Okay, then we would go to the hands-on part and pass over to Thorsten.
And then you can. So I will just select this model that we just exported. Then you get a nice preview with some general information about the FMU. So it comes with source code. That's what we selected in the dialog before. It has Windows 64 binaries. That's platform I'm on. We'll see in a second how to compile for different platforms. Here's the variables. So it's pretty much a black box. It just has the inputs and outputs. It's just a property of the GRT model. It just doesn't expose the parameters that get compiled in. The Daimola version we'll see in a second is much more flexible. You can change the output, or just leave it like this, and then you have some advanced settings. Like there's documentation on this if you go here that explains what all this means. For the sake of this tutorial, just click OK, and then you get the inputs and outputs as expected. And yeah, this is what you would use to connect to your existing system to integrate. So this round trip doesn't really make sense because if you're like working in a pure MathWorks environment, you would probably use S functions. But I'm just showing it that you can go either way. And also this doesn't have to come from Simulink. Obviously you could use Daimola FMU in Simulink and vice versa.
What's perhaps also important here, for example, this mask, this is completely created, for example, the inputs output, this is directly created from the XML file, so you don't have to create this. So the FMU contains all the information that is necessary to create this.
Exactly. I'll just leave it open just in case we need.
Yeah, I have one more question.
Good.
Sorry. So now we have imported this FMU, and if we want to export it to a C file, or if I want to export this like using Simulink coder, is it possible? Because importing DLL, it's kind of a binary. We imported it.
So the question is, can you export a Simulink model that already contains FMUs?
Yes.
Yes, you can. With FMI kit you can. I think with the native solution you can. But you can actually make nested FMUs. So you could actually, with FMI kit, you can make an FMU from a Simulink model that already contains FMUs, yeah, you can do that. However, this would not be a source code FMU. I mean, the outer shell would be source code, but the inside needs to be pre-compiled, but yes, it's possible. It even works with Rapid Accelerator, for example, even with the binaries, because like what we just looked at here, you can tell by clicking here, it's an S function. And this is actually a source S function. So yes, you can make GRT models and Rapid Accelerator models using this binary FMU. And there's also ways to include the source code into your final model, so you have like one big binary that does not depend on any other binaries. That's also possible. But I think that's going a little bit too far. That's very, very technical, but yes, it's possible. Sometimes requires a little bit of work on your end, but it's generally possible. Okay. Now validations. That's a really important one, I think, especially for people in the industry validating FMUs. So we've made a nice website, which you probably already know. There is a link to the validation page. So there is a couple of options. Easiest one is the FMU check. So let's just go here. So it's online. All you have to do is click it. You could actually use this on your iPhone if you wanted. All you have to do is select the FMU. Just yeah, let's use the Simulink one. Let's see if it's valid FMU. So it's already been uploaded to the server. Obviously, you have to agree that we check this FMU and unpack it on our end because you're uploading to the internet. I think it makes sense. There's a short list of what's being checked. And yeah, seems to be okay. You can also view the variables, get some overview, also what's inside the FMU. We'll see a better version of this in the GUI. I'm just showing you what you can do here. So that's pretty much it. Just as long as you have this green box here, it's all good. If there is any problem, it will be reported. But this is, for the most part, a static check.
Just a little question. Then when you are using this FMU checker, you are ensuring that you are compliant to the FMI standard rules?
Some rules, yes.
Some rules.
To the best of the ability of the tool.
And here, in this case, only the XML is checked.
No, it's actually more than just the XML, but it's a static check. It's not a dynamic check, so we're not loading the DLLs.
Okay, so it's let's say a first step to validate the FMU, but it doesn't ensure that.
Put another way, if you fail here, it's definitely not valid, but only because you get the green checkbox does not mean it's a valid FMU.
Okay.
So there's still, as I said, there is infinitely many ways to screw it up, but it's a good start.
Okay.
And this is based on FMI. So if you have FMI installed, it's pointless to use this web service because you already have it on your machine. But it's just very convenient for people that don't want to install or can or are on the move. You can just use this version. Again, it's linked from our website. Yeah. Okay.
So the source code is somewhere there. If someone wants to use this validation logic,
you can. Actually, the whole website is open source. So like even this web interface is open source. FMI is also open source. So it's spread across different repositories, but you'll figure it out. Actually, FMI comes with its own web app that looks like this, but it's way more powerful. You can even like run a simulation and plot it. Maybe we have enough time to look at it. If there are any questions, just get back to me anytime or meet me at the booth today, tomorrow, day after tomorrow. I'll also be here on Thursday for the FMI meeting. It's probably also good to discuss things like this. It's just a random selection of things you can do, but there's so much more that we just can't cover here. Okay, does everyone have FMI installed now? So I hope so. So let's just bring up the GUI again. To me, this is by far the most comfortable way to work with FMUs. You can just go this way. You can also drag and drop an FMU, but since I already have it open here, I'll just open the drive. I'll just keep this list here so I don't forget anything. First thing you want to do is, so you don't have to type this blah blah all the time, you can go here, tools, at least on Windows, you can create a desktop shortcut, and you can also associate FMU files with FMI GUI, so you can just double click FMU files. It's optional, but I would recommend it.
Please zoom in and go into where you are in. Can you zoom in somehow?
Not really. Is it like, can you maybe move forward if you can read it? Yeah, I'm sorry.
But they're not recording, right? This is just.
No, the screen's recorded and the audio, but not
recorded.
Yeah, so this is all recorded, so you can look at it later.
Great.
Yeah, so validation, as I said, it's built in, so you can just click validate here. No problems have been found. Perfect. Here you have some detailed information. If you move your mouse pointer over the image that comes with the FMU, it's a little bit bigger. So this FMU is I already pre-compiled all the binaries, but I'll show you again how it's done. So as long as you have the source code, you can actually go to Tools, Compile Platform Binary. If you have Visual Studio installed, you can compile for Windows 32 and 64-bit. You can also compile for Linux if you have WSL installed. So you can directly cross-compile from Windows using WSL. If you have at least, I think there's developer tools or something, so you need a GCC to make it work. But that's very convenient because then you can directly deal to someone else that just has a Linux machine and they can run the FMU. Obviously you need the matching binaries. There's some caveats with Linux, especially the glibc, which is kind of a pain in the backside because it has to match the version you're running. So if you compile on a very new system and go to the cloud, they usually use a very old system and then you have to compile it again to make it work, but yeah, it's just the way it is. On Windows, typically you don't have any problems. Even if you use the latest Visual Studio version, it will still work on the oldest Windows you can find. Optionally, you can also remove the source code for IP reasons or what have you. you can create a Jupyter notebook. That's what we're going to do in a second. You can create a CMake project. That's for the hackers. Very useful, but we don't have the time to do it right now. But again, just get back to me. I'll be happy to show you how to do it. Remoting, that's really advanced. Not covering it here, and that's for the Modelica import. We'll also not cover this here.
And to see the source code, you need to go to the FMU zip and zip to see the source code.
You mean the source code?
Yeah.
Yeah. I think I've linked it here. So if you
Yes, but in the FMU itself, there is the source code now, no?
yeah, so this FMU, like both the Simulink and the Daimola version, come with source code. You can tell here because it says platform C code. So C code counts as an extra platform. Obviously, you cannot execute the C code, but you can compile for the different platforms.
Torso, we don't have the binaries for Mac, right?
Yeah, but if you have Xcode, you can actually compile on yourself if you want.
Yeah, okay.
Do we have Mac users here?
One user. But
Yeah.
okay.
So if you can bring up the GUI, does the compile? Can
Maybe
on a Mac it should say Darwin here. Darwin is macOS.
I'll use Open Modelica for export one from the machine.
It comes with some source code, but it's not a valid source code FMU. That's why we're not using it in this demo.
No, I mean to export an FMU with the binaries already.
Probably, yeah.
That's the way I can.
But I think, does Open Modelica run on Mac? Probably.
Yes.
Yeah, it does? Okay, perfect.
Yes.
Can you open the download the
All I know is they have some weird dependencies on their like MSys compiler system they're using, so it comes with some source code, but it's not a valid source code FMU. Unlike the other two we have in this repository. But again, you can just use the Daimola one. It should compile anywhere, even on a Raspberry Pi, for example. I tried this out. Okay, back to the agenda. So you view the model info. Then there's also documentation tab. So yeah, so this is some generic documentation here, listing the licenses and software and what have you. You can put more information in your model. This particular one doesn't have it, but you can have some nice HTML file in there that you can view. Then this one's also really handy, so if you just want to have a quick look what's inside the FMU, you can just scroll through here. So it's mostly documentation, but also source code. This is all the stuff you need to compile it from source. This is the image we saw on the first page here. And this is the model description. We'll look at the model description if we have time. But the model description is the file from which all the information you see here is extracted. So this here is all in the model description. And as you can imagine, it's a very big file, especially for larger models. It can be several megabytes. Okay. So yeah, let's simulate. So we have the choice, model exchange and co-simulation. For now, we'll just stick with co-simulation. Because you asked this 1.0 seconds, this comes from the default experiment. So that's what you bake into the model. You can change this to 10 or 0.1 or what have you. I'll just click play here, and then it's not very exciting. We get 0. It's kind of expected. That's because our just collapse all because this here. Low torque. I think the W is the desired crank speed is 0. If we change this to 1, still 0. No, the voltage is the interesting one.
That's the output.
Yes. Yeah. I see. Like so. So it's slightly different now. Okay, but that's not very exciting. Of course, we can set a start value for an input, but input makes more sense with an actual input file. So let's just make one. And you can make one from scratch. FMI GUI helps you with this. If you click this down arrow here, you can say new input file. And then I already have one, so I'll call this in2_2. And what it already created this file, and we can open this in the default application. And what it does for you is it's figuring out all the inputs and creates the first line for you. But I've already created another one that has some reasonable input. It's actually exactly a copy of the Modelica model with the steps at 0.1 and 0.5, I think. So let's just use this. So I'll just delete the _2 here. So we're using this preview file. By the way, this file is in the part 2 directory, so you can have a look at it if you want. It's just a CSV. And there you go. And what might also be interesting is to change start value. I'll just switch to the list view. Christian, do you recall the inertia value you wanted to change? I think I took a note here. Load inertia 1.j. Filter this a little bit. Load inertia 1j. So default is 1. If we change this to 10, which makes it a little bit more, you say like sluggish, then run this again. You can immediately see the result. What's also really nice for debugging, you can also lock the FMI calls. I'll limit this for this demo. I'll limit this just to 10 so we don't get that many. Obviously, you can run this with any number you want. If we run this again, obviously this is very chunky here because we only have 10 samples. But you can see the whole FMI call sequence. So these are all the calls from to the FMU. But I think that's one thing you brought up. So it's the set value, see like set real, all the value references. So these are the actual input values. Then we do a do step with a certain communication size. In this case, it's 0.1 because it's a 10th of 1 second. Because we selected 10 to split this second into 10 intervals. By the way, we can also say we use a fixed interval, so we could also go with like 0.01 here if we wanted. And then we get the output. In this case, it also has integers and booleans. They're not really important for this demonstration. And then the next one starts with set real, so it's next input and so on and so forth. Okay. Validation, compilation. Again, so if you want to compile and have everything installed, you can do compile and then select the platform here. Log debug information, call sequence, we got that. So yeah, so one really interesting thing is you can also generate a Python notebook from this. So you go tools, create Jupyter notebook. Jupyter notebook I should say. So it's a Python-based Jupyter notebook. I've already created this here, but I will just override it. So I'll just go save here. So it should not ask you, but I already have it, so I replace it. And then I can start it by clicking yes. If you don't have all this and just Jupyter installed, you can also use the file and start it directly. And what it does is it's taking all the information from the XML and generates this nice file for you. So yeah, you can just instantly run this. I just press Shift Return to run the notebook. You get exactly the same output with the nice labeling and units and all the stuff. And so now we want the input. So what we can do is input equals read CSV drive in.csv, and then we can use this here as an additional variable and run this again. And you see, like before, you have this peak here, and if we change this parameter here, again, the units are optional, but for consistency, I think it makes sense to use them. If we run this again, you see it's exactly the same result as before. You can also like write the result to, you don't have to plot it, you can write it to CSV, do everything you can do in Python, use this for machine learning, what have you. Endless, limitless possibilities. Okay. So yeah, do we still have time for the reference FMUs? I think that's really interesting. Perhaps for most people, so I'll just go through this really quickly. So how do you download them? Google reference FMU, so you already have it here. Then you go to releases and select reference FMUs. So it comes as a pre-built zip file. You can build this from source if you want, but you can just use them from here. I'll just quickly extract them. So what's inside? I'll just bring up a new console. Okay, so that's the content. You have the FMU sim binaries for Darwin, that's macOS, Linux, and Windows, all 64 bits. Darwin is actually ARM and so it should work on the newer M1s and M2s.
Just confirm.
Yeah, I've never tried because I don't have one. They wouldn't buy me one.
Yeah.
I'd love to have one. So yeah, so what we do is let's just go into the FMU sim Windows directory, CV. So there's just one executable, it's called FMU sim. If you run it, it will give you a rundown of all the things you can do with it. So there's some more documentation on the reference FMUs homepage. We're running out of time, so we'll just get going. Yeah, so let's simulate this FMU. And by the way, like the source code might be really handy for you. If you're trying to export an FMU or want to integrate import, there is a reference implementation for 1.0, 2.0, 3.0, both model exchange and code simulation, also some examples even for scheduled execution. It's all in your reference FMUs. All BSD2, so you can just readily use it in your even proprietary software. So, FMU sim, simulate. I'm doing this right. Yeah, let's do the bouncing ball. This is probably the simple one. So that's one folder R. Let's do 2.0. Doesn't really matter. There we go. Not very exciting because we just simulated it. But what we could do is we can do log FMI calls. So now we get a nice list. It's exactly the same, except this is all C code. And you can even, like, it comes with CBODE, so you have an advanced variable step solver included. Yeah, there's a couple more options. Let's just bring them back. You can set, obviously, start time, stop time, input, output interval, start values. You can use an input CSV also for arrays. That's really interesting because a lot of tools can't handle this at the moment. Output files, so you can write the output to a CSV. Yeah, so these are a couple more advanced options. Solver is only relevant for model exchange, so you can choose from Euler. Currently there's only the two, Euler and CBODE. Yeah, the rest is a little bit more advanced. You can even save the FMUs that we restored at a later point. Okay, I think we're running out of time, but we're finished.
Are there questions on that part? Then we would pass over to Claudio and Maurizio for the third part. So this is
Good. Okay, so we're moving on to part 3 now. This first part will consist of a live demonstration using a graphical user interface to connect FMUs and run. This is an academic tool. Expect some hiccups installing and so on. But this is just a very minimalistic interface to show you how to connect different FMUs together and run a simulation. Then the second part will be delivered by Maurizio, where we will go into more advanced techniques to connect different FMUs where you have more control over how you're conducting the co-simulation. So I'll be following this guide. This is what you see on the README file of our public repository. I will give the demo, and Mauricio will go around and help you. He's quite an expert on the application, and he's going to run around and help you if you have any issues. Yeah, we are recording. So the first thing is to find the application. We can just Google InterCPS application. We'll find a GitHub repository containing the application. In there, we go to the releases folder, and you can download the latest release from July this year. And it should work on your platform, including Mac. By the way, do not be afraid if you at some point fall off the wagon. We have a video of this same demonstration online already, so you can follow at your own leisure. As I download the application, you can find the executable for Windows. This is the best, doesn't require installation, so maybe those who have who do not have administration privileges can still run it. As it downloads, I will just do some pre-check on your system, or I ask you to do a pre-check on your system, check if you have Java installed, because that is one of the prerequisites to run this. So I will open a terminal. PowerShell works, but you can also open the command line. I'll open both. And what I ask you is, if you type Java -- version, you should get something Java 11 or above. Then it should work, and it's the same on both terminals. If you do not have, then reach out, make eye contact to Mauricio, and he will help you install Java if you wish to get your hands dirty with the application. Otherwise, just follow along. Okay, having this preliminary check done, once you download the application, I've already downloaded it, so I'm just going to execute the binary. Oh, nice, running already. Try launching it. It's a bit slow, but if you double click on the binary, to be on your downloads folder, I like to put it on my C because just use it like that. I guess there are previous scars where there were spaces and it caused problems. This is what the application should look like the first time you run it. And we go back to my script. Thing we need to do is you can go to the download manager inside the application. So this application allows you to select the FMUs and select how they're going to be connected, but it doesn't run the co-simulation per se. So you need to download the co-simulation orchestration engine to run the co-simulation. So if you go to the download manager, you can select the latest release by just clicking on the number, and it should scroll you down to the bottom of the page with a number of different tools. This was an application created as part of a European project where we tried to unify a tool chain to do the model-based systems engineering, and so for historical reasons you can download many tools from here, including Open Modelica. And we regularly try to make these tools work together fine using FMI. So you can download this Maestro 2 co-simulation orchestration engine. The same demo should work if you download the co-simulation orchestration engine version 1. So if you're for some reason having problems, you can try one or the other. If you press download, it should go into some page that shows a little download bar, and then it should tell you you're good to go. After that, you can go down here to the COE console, and it is offline, so there's a red light, and if the gods are good and you press launch, then there should be, it shows here the command being executed in the terminal. So if you're having problems, you can try running this on the terminal. But if the gods are good, you should see some info messages, and basically this should turn green. And that means the orchestration engine is ready to run stuff. Everyone has a green? Or, yeah, okay. Yeah, so the preliminaries are done. We are ready to start connecting FMUs and running. So we'll create a project now. We go to File, and we do New Project. I'm just going to call it FMI Demo. And I'm going to select some root path of the project. Well, I could have it on my Documents folder into CPS projects. This could be something. So I will create a folder here called FMI Demo, and select this folder as the location of this project. Press Create. It should create, if we visit that folder again on my, try a different way. Oh, sorry, it tries to connect somewhere, and so it takes a long time. You might actually be able to right click on these FMUs and show in folder. This will show you the folder structure of one of these projects. And you can see this is where the FMUs should go that you want to run, and this is where the configurations will go. I'll show you in a minute. But this is where we want to put the FMUs. And now the FMUs we are going to use are given as part of our repository. I think it's on GitHub. FMI Beginners Tutorial. You can download these FMUs under Part 3. Under Part 3, I already made available for you an Into CPS app project. So you could open this project in your app if you wish, but if you want to do it by hand and see what's going on, then you can get the FMUs from here. These FMUs, as Torsten showed, they've been compiled to all major platforms, maybe with the exception of Darwin, and so you should be able to run them. So I'll just copy these. And I will paste them here. And returning to the app, I should see the 3 FMUs there. Sorry. Yeah, now I will create a multi-model. This is where we say where are the FMUs, how many instances per FMU do we want, and how they will be connected. So I'll create a new multi-model. I can leave it multi-model new. And for now, there's no configuration. I'll maximize the window. And so what I want now is to start to edit a configuration, start adding FMUs. So I'll add an FMU. I have 3 FMUs, so I'll add the controller FMU. I'll give it a name controller and select it as the FMU controller. If in your application it says not supported, it's doing a preliminary check on the FMU whether you have the compatible binaries. If not, then we need to talk. Drive FMU. Select the drive FMU and stimuli. Yeah. So I've got the 3 FMUs, and now remember we can have multiple instances of the same FMU. So if I could have multiple instances of my controller FMU. I cannot think of a good example of what two controllers would have to do with the same implementation, but there are examples out there where it makes sense to have multiple instances of FMUs. So I will create an instance of the FMU. I'll just call it control. I will select the drive and create an instance of this one, which I'll call drive. And I'll create an instance of this one, which I'll call input, because I'm not sure how to pronounce the word stimuli. So we've got 3 FMUs, 3 instances. Now we're going to connect. So this is the control instance of the control FMU, of the controller FMU. It's got an output V, and as mentioned before, the application is looking into the FMU, the model description file, and generates automatically the outputs and inputs that you wish to connect. So the controller output has an output variable V, and then we can check that just to show you. You can open this with 7-zip, or you could open it with FMI GUI and open the model description, and there should be an output variable, a scalar variable with an output V. So just doing a sanity check here. Good. We'll connect this output will be connected to the drive FMU. This is a typical control system. So the controller is connected to the plant, and the plant will be connected to the controller, and there's some input that's connected to both controller and plant.
Just a question. Is
yeah.
it possible to make the connection automatic?
Not in this application.
Mm-hmm.
I think there is ports and icons, right? There are some.
Some tools today, even with FMI2, they have heuristics. For example, if you have matching names, they suggest to connect. So this is up to the importing tools. And with the terminals, from the terminals and icons, you could, for example, define more or less standardized tools that match together. So this could be also defined domain specific in a layered standard. That, for example, you have in hydraulics, you always have matching quantities that you can connect with one line in your graphical tool or so.
Okay.
All connections.
And then can you also perform, let's say, consistency check regarding the units, for instance?
That's also up to the tool, and it's recommended to do that. And good tools do that.
And the information is there. So the information in the FMI standard is there is enough information to allow you to do that.
Okay.
Yeah. Right. So we've got yes, this is connected. The drive has an output, which is the angular speed. It's connected to the controller. And the input has 2 outputs. The load torque, this is connected to the drive. If you recall, let me just bring up the slides from the first part that Christian showed you. Might help you as a reference. Yeah. If you squint, you can see the controller output is connected to the drive here, and there's this load torque being connected between the stimuli FMU and the drive FMU. And so this is what we are connecting. We're creating these connections between the colored blocks. So the load torque goes into the drive, and then this W desired goes into the controller W desired. So everything is now connected. We can set parameters here if we wish. Someone asked, can you configure the controllers? This is an example where you could go here and change the inertia, for example. You can get an overview of the connections here in a very simplistic interface. A note, this application does not allow you to make a CSV file with an input profile, right? So that would have to be inside an FMU if you wish to make this work. Many other applications support the ability to import a CSV file or define any other input. Okay. Yeah, we are good. There's no simulation parameterization here. We're just defining the system model, right? That's why it's called a multi-model. Now we're going to create co-simulation configurations by right-clicking on the multi-model and then creating a co-simulation configuration. In this co-simulation configuration, there is some default stuff, but as far as I remember, the end time was 1 second, right? And the time step was 0.01. So that this is our simulation scenario. We are using a very basic algorithm that calls the do step function with a fixed time. So every FMU advances in lockstep over time. There will be roughly 1,000 steps in this simulation. There's some logging definitions. If something goes wrong, you can enable this. It's all enabled by the FMI standard interface. You can define some other more advanced algorithms here, but we're not so worried about that. We want to plot some things. We want to see a plot. So I want to plot every 0.1 seconds. So my plotting will do every 10 steps. I'll plot something, and I want to add I want to plot the W versus W desired. That's our criteria. This is what we care about. Maybe we can create another plot just to demonstrate the output of the controller.
Just a question, please.
Yeah.
You are performing co-simulation, so
Yeah.
my understanding is that each FMU is calculating its own, is solving its own equations,
Yes.
and then when the convergence is attempted, then you share your data according to the time step.
We're not really doing convergence.
Mhm.
We're just assuming it converges after one step.
Ah, okay.
Yeah. So we're doing a weak coupling co-simulation.
Okay.
Yeah. We can talk about this successive substitution is an attempt at ensuring strong coupling for FMUs that support it.
Okay. And how do you ensure the accuracy?
We should discuss that. That's an interesting research point. Yeah, we've done. We've tried different methods.
Okay.
Okay. In the next part, you will actually see how this is being done in a very simplistic way, and you can even attempt different ways to do it. We can opt for plotting, storing some extra variables in the CSV, but by default, all the connections are stored in a CSV file. And there are some other options. We'll skip those for now. Good. So after this, if you have the orchestration algorithm running, then we can press simulate. If the demo effect does not kick in, then we get results. Yes. Here you can see the two variables. That's the first plot. The second plot is the controller output. So we've run our first co-simulation involving two FMUs with no headaches. You can open the results, and in this results folder you can see this results folder is stored automatically inside the Into CPS project, inside the multi-model, inside this co-simulation. It's timestamped, and in principle we ensure full traceability between the co-simulation configuration and the results. That's why we're storing. If you open this on your favorite text editor and you inspect these results, okay, you need to format a few things, but we're using open standards to represent the co-simulation configuration here. And if you go to the simulation, so I need to format this for your own sanity, and you can find here the full parameterization of the co-simulation experiment that was used to generate those results, right?
Do you also support SSP standard here? Because I think that would be, for explanation, that would be a use case for SSP standard.
Yeah. Okay. No, we don't support. No, this was made 4 years ago or something. It was before SSP. Yeah. And you can find the results CSV, so you can get the results to process, to do something with them. There is also a zip file where this is in case things go wrong the logs of the FMUs are there, so you can start debugging and investigating if something goes wrong. So we run our first simulation, no headaches. Now let's try getting some headaches. As Christian mentioned before, the co-simulation step size is a very important parameter, right? So now let's see how important it is when we start changing it, and let's see how the results change. So I'll do just a quick poor man's approach to compare these different results. I will just put this on some document. I can compare it before and after.
Yeah, quick question.
Yeah.
So now that you mentioned time, is there a time delay between subsequent FMUs? I
Sure.
would expect it. Okay,
Yeah.
so it happens.
Yeah, I'll
Because
show you.
now it's safe because the time step is very small with respect to the whole range.
Yes. I'm glad you're one step ahead. This is exactly what I'm going to do now. So we're going to change the time step in different phases. I'll put it 0.05. Save. I have the same. It's important to have the same configuration for the plotting. Yeah. So we can then try again. This will create a new batch of results, and it's hard to tell the difference. So I'm going to take a screenshot again and just paste it on my whiteboard, and hopefully I can align these two nicely, and you can see, okay, there seems to be some differences here, right? Some problems already. Let's carry on.
Just to clarify,
Yeah?
you're running both FMUs from initial conditions together and then rereading instead of running them serially?
Oh.
You mentioned it and I wasn't sure I followed.
No, so the simulation, what we are doing is, at every co-simulation step,
Yep.
we are getting the outputs of each FMU, and there are 3 FMUs. We set the inputs according to the connections in the multi-model, and then we call do step with a step size of 0.005.
Okay, but they're all run from at the same instance.
Yeah.
From those conditions, they're all run in parallel with each other.
Yeah, they're running in lockstep, and then after 0.05 seconds, we repeat the process. So we keep this loop until the end of until reaching the time 1.
Are there other options if you wanted to run them serially for one reason or another?
Generally, I haven't seen. I mean, you do not need FMI to run things serially because you can export them as CSV or use whatever formats to store the data. FMI is great for when you have a feedback loop. So in this example, the behavior of my controller depends on the behavior of the drive, and the behavior of the drive depends on the behavior of the controller. It's only when you have this behavior interdependence, this closed loop dependency, that it makes sense to use FMI.
Okay.
But it's a good question. It's
One more question.
we took that for granted.
With regard to this, so if you have several FMUs that you run in parallel today, then run on the separate CPU. Can you distribute them in a way that they will it also work then with multi-threading that you would use then several threads on one CPU?
We've had examples. In particular, I think the Intro-CPS app actually supports parallelization. If you wish to take advantage of using multiple threads per FMU, but it's definitely a use case. I've seen people use it.
Okay.
So yeah, perfectly possible. Yeah.
I also have a question.
Yeah.
As far as I know, there's a similar post-simulation tool called Modelica
Yeah.
like this. So is this Intro-CPS is also available to post-simulate with some heavy model like autonomous car and some kind of MBD model?
We haven't tested, but as long as it implements, as long as it's an FMU, it should be fine. Yeah, it shouldn't. In theory, it shouldn't affect the application. Naturally, we've had situations where even though multiple tools conform to the FMI standard, it still doesn't entirely work.
Is this tool free?
Oh yeah, this is available online. Yes, we use this for education mostly for people to learn about co-simulation. Yeah.
Yeah. So Yeah, the internal time of each FMU is 0.001 seconds. And now you are changing the time of the communication between these
so
FMUs.
I think I need to bring this. So what's going on is, if the red is my controller and my drive is the black, then what's going on is at time 0, at time 0, I'm getting an output from the controller, and I'm providing that output for the drive. So the drive gets the value for this controller. I'll represent it like so. Then we are calling do step on both FMUs. What happens is the drive is a continuous system, so it will use internally some numerical solver to estimate the continuous behavior of this, which may mean if this is 0.005, as in that example, then the controller may do it may do multiple steps of variable step size, for example, like so, and it terminates here. For all intents and purposes, from the point of view of the drive, the control output that was used was this one and kept the same during this time interval. There are more advanced cases where we need an input to vary, even within the smaller interval. But for our intents, this is how it works. Now, when we communicate with the controller gets this value, right? So this is the communication step size, or the co-simulation step.
So then we have two numerical errors. One is the local ODE, and then
the input approximation error. So this error, if you have, this is particularly more, it's more acute when you're coupling multiple physical systems, because they will assume that this thing is a constant during this interval, and I think Martin Arnold, I don't know if he's come to the conference, but he has shown a while ago that actually this input error drives the co-simulation error, is the main factor behind the co-simulation error. You can pick whatever solvers internally, that's great, because they're typically orders of, they work in accuracy of orders of magnitude higher than this co-simulation step. So they're much more accurate. But so the problem is this co-simulation step.
And if we tune down that step to the solver step, then
theoretically
it's more expensive.
Yeah, and in theory, as you take the limit of this co-simulation step towards 0, you should get more and more accurate results. They should approximate.
This is expensive because you then have to reinitialize internal solvers. If this is a higher order solver, then it takes very slow steps and so on, and this slows down simulation. So you should make the communication step as large as possible, but as small, so that you get enough accuracy.
That is some background information, because at the beginning we were talking about model exchange. We have one solver and co-simulation. And the advantage of co-simulation, if you work together with companies, you can guarantee local stability. And that is a big advantage. Otherwise, with model exchange, we are normally lost if you want to guarantee anything. So in industry, we normally only use co-simulation.
Thank you. Let's so let's break the simulation, right? Let's increase the step size. We will increase it to 0.01. Save. Run. Okay, starting to look pretty bad. We see some overshoot, which we definitely haven't seen before. So at this point, we're in dangerous levels because we're thinking our controller is bad, but it's actually our co-simulation configuration is invalid. So this is something to look out for. And if we continue increasing the step size, we're getting faster and faster co-simulations, but worse and worse results. And here it is actually unstable. All right. So this is this concludes the demo part, and now we'll move into more advanced ways in which, for example, you can automatically determine what step size you wish to get, and so you can quickly make different experiments. So to be clear, all these FMUs are being run in the same process.
Ah, okay.
Yeah, these experiments they're totally independent of whether you want to parallelize.
And they are computed sequentially. And not
Yeah.
Okay.
Yeah, there is walk-up time and there's simulation time.
Okay.
So in simulation time, they're computed in parallel, they're in lockstep.
Mm-hmm.
But on the computer, they're literally in sequence.
Okay.
Yeah. Thanks. That's a good confusion. Yeah.
But this is up to the tool, so there are other tools who could even distribute remotely or whatever. So.
Okay, so now we can move to the second part of part 3. So now we will run a tutorial on connecting multiple FMUs with into CPS from command line interface. So on the GitHub, we are starting on this part 2 of part 3. You can find this, in this folder you can find a Jupyter notebook. This is supposed to run smoothly on Linux system. So my suggestion, if you don't have it, you can open this notebook in Colab, as I am going to do. And if you don't have a Google account, you can still follow using this Colab. And basically, now we will repeat something that you have already seen with Claudio. And basically, in this notebook, the first part we will run some preparations. So I will run cell by cell. So the first cell is, of course, I will allow the execution. The first cell is just importing some dependencies related to Python. Okay, then the second one, I am downloading the GitHub of this tutorial with all the FMUs that we need. Then some preparations, so I'm moving to the folder of part 3 of this specific tutorial, and I am giving execution permission to the executable that is named coe_jar. So now, first we will run a co-simulation, a scenario with only one FMU that contains the whole system, and we will use this scenario as a baseline. So what you can see in this cell, I'm just loading the file single FMU scenario.json, and you can see it if you run. So this is the JSON. This JSON has been automatically generated by the into CPS application, so you don't need to write this one from scratch, of course. So you can see some informations that you have already inserted with Claudio. So for example, the type of fixed step algorithm and the step size 0.001. Since we have only one FMU, we explicitly say to the executable to log the variable of the torque. And then we have also other informations like where to actually find the FMU. In this case, you have only one FMU baseline, and this is the relative path. And then we have also some information about logging and override log level. So we have the minimum information for this tutorial. Then we prepare and execute the coe command. So basically, you have downloaded the Maestro or the Maestro 2 or Maestro 1. In this case, I'm using Maestro 1. So the command is easy. It's just a Java jar. So it's Java -jar, the path of the executable. Then we are adding some options. With the -o, we are asking for a one-shot. So we are from command line. So we are just running one co-simulation, and then the process, the COE, will die. We are specifying the configuration, so this is the JSON that we have seen before. And then we are giving start time and end time. So we will simulate from time 0 to time 1. So we can execute this one. Yes?
Can you show again how to open the Jupyter Colab?
Yes, so in order to open the Jupyter Colab Jupyter Notebook on Colab, sorry. So you can go on the GitHub of this tutorial. And in part 3, sorry, not in part 3, on the README, you can see in part 3, so this is the first part that you have done with Claudio. In this second part, you have a link, so this link drives you directly to the Jupyter Notebook. On top of the Jupyter Notebook, you can find the Open in Colab button. So you just need to click on this button, and you will. Now I cannot do it because I have already Colab running. And then you will go to this Google Colab. So if you are having problem, just ask Claudio and repeat this operation. So we have run this command, so you can see we have used the version 1 of the COE, Maestro 1. It has been initialized. This is the session ID. It took roughly 1 second to run the co-simulation. Then the session is finished because it was a one shot, so only one co-simulation. And the output has been written in this file, output.csv. With pandas or any other tools. In this case, we are using pandas because we are using Python. You can open the file, and here you can see step by step. So, for example, time 0, there was no time step was executed. Then we executed a time with a step size 0.001. We moved to time 0.001, and again up until 1 second. In this case, it stopped to 0.999. And you can see this is always the same model. So the torque started from 0 as an evolution, and in the end it was 10. We can plot it with matplotlib. And here you can see more or less the same behavior that you have seen with Claudio. So this is our baseline scenario. Now we want to run the decoupled scenario. So we will use the 3 separated FMUs. So this is the new, the different JSON. So we have the 3 FMUs, their path, their location, relative path. And then now we are giving also the connections. Again, this JSON file has been automatically created by the Into-CPS application. You don't have to write it. And this one you can see the connection that you have created with Claudio. So from stimuli to control, from stimuli to drive, from control to drive, from drive to control. The same variables that you have seen before with Claudio. And then again the same options. So in this case we are not setting any particular parameters. Same algorithm, fixed step, but with the same step size. Again, we run the co-simulation with the same command, just giving a different configuration JSON file. And we have also some control if something goes wrong. Okay, so again, now you can see, now we have more FMUs, so with their connection. This means that now the execution time is higher. It took roughly 15 seconds for this co-simulation. The output is always stored in output.csv. So again, you can use Panda to read the CSV, and matplotlib to plot the graph. And again, we can see more or less the same behavior with respect to the baseline. We can see that it is actually following the desired torque. And now we will actually directly compare the baseline with our decoupled scenario. So what are we going to do? We are going to co-simulate both the baseline scenario and the decoupled scenario at the same time. So we can prepare the, the JSON, and you can see we have the 3 decoupled FMUs and the baseline FMU. So we are loading all of them. We are connecting the 3 FMUs that compose the decoupled scenario, and we also have the baseline. So they are basically running in parallel because there is no connection between them, and so we can compare the at runtime the 2 different behaviors. So since baseline is not connected to any baseline FMU is not connected to any other FMU, we need to specifically say that we want to log the variable torque W, that is the output of the baseline FMU. We can run the co-simulation with the same command. Now I think this one might take a bit more than 15 seconds. This is what we expect. Well, sometimes it gets faster, and now it only took 10 seconds. Again, we can see the results. The results are always stored in the file output.csv. Of course, it is possible from command line to choose a different file. Output.csv is the default choice for saving the results. There is an option that allows you to change the name of the output file if you want to keep trace of all your co-simulation, of course. So now we have the CSV of the whole simulation. We can plot the difference between the baseline and the decoupled scenario. We can see that there is some difference here at this point, and if we can zoom a little bit more, you can see that the 2 lines, the torque of the baseline scenario and the torque of the decoupled scenario, mostly overlap, but there is a little difference. So we can define a function to measure the error. In this case, we simply compute the sum squared differences over time. So we can, and we are taking this data from the log, and we get the error, which is 7.2 radians per second squared. And we can, watching from this graph, people expert in the domain can assess if this error is low enough, or if they want to work on this error and reduce the error.
So we know where does this error come from exactly? Like, we know the reason of the error?
The reason is the one that Claudio showed on the whiteboard. So there is a time between the connection. So one FMU is sending output to the other FMU, but while it is evaluating, while it is performing a step, the other FMU doesn't know the actual behavior of the variable and has to infer it, or in some simple case, it takes as constant the output of the previous step. So in the baseline, since the whole system is within the same FMU, every component knows the exact behavior at every instant of the co-simulation. In this case, there is this delay of one step, which leads to these small differences. And of course, the smaller the step size of the co-simulation, the smaller is the delay, the smaller is the error.
Can we know a priori before we run run the simulations, how much even mistake or error we're gonna make at some instance in time?
Before running the co-simulation,
It is possible if you know the accuracy of the internal solvers and you know the order of the extrapolation being used in the inputs. Then the order, the accuracy order, the order means the rate of convergence of the error as you decrease the step size to 0. It's not going to give you a concrete number. It's just going to give you how this error behaves as you change the error step size. That order is typically coincides with the largest order of the group of FMUs for their use in their input approximation functions. So basically the weakest link in the chain is the one that really drags down the consolidation accuracy.
Okay, so now we will see how the step size impacts the accuracy, the error of the co-simulation. So we will define a couple of support functions. In this case, I want to. With this cell we will run a lot of co-simulations. So allow me to first trigger the execution and then explain. So we have just a couple of support functions to read the JSON and change something, and just run different simulation with different step size. And basically with this line we are running the co-simulations.
Yes. I think due to the discussions we are a little bit running out of time. We should a little bit speed up if possible.
Yes, it's just the time that this cell finishes.
Okay.
It will be just
May
some
ask,
7 minutes.
Mr.
Yes.
Meanwhile, does the tool defines the consistent initial conditions?
This tool.
Yes. Okay.
It exchanges data in the initial part, but if you mean really reaching convergence, then it only does so, not a command line. Well, there's a command line option to do it using stabilization, but I wouldn't swear by it. We have not. I think tools like Daimler do a much better job at getting this initial problem.
Thanks.
Okay, so basically in this case we are running co-simulation with trying 4 different step sizes chosen by this function, and basically you can see the 4 values here. So we are trying from a very low step size 0.0001 up to 0.001, and what we expect and what we will see when all these simulations, co-simulations end, is that for smaller step size we expect smaller error but higher co-simulation execution time. So the actual time required to run the co-simulation. So in this case we are both we are taking as information both the error and the execution time. The execution time is simply taken by logging the time before running a co-simulation and then taking the time again and removing the one that we had saved before. So this is done. We can plot the results. So basically we can see that for step size, the smallest step size, we also have the smallest error, and as the step size increases, the error increases. At the same time, as we predicted, for smaller step sizes we have the highest execution time, and then for smaller step sizes, for higher step sizes, we have smaller execution time. So the values you can find here. So for example, we started from 0.001, the error was 7.2. From 0.0001, the error was 0.5, so there is a significant reduction. But also the execution time increased a lot. We went from 15 seconds to 75 seconds. And of course now you can play with this. We don't have time here now, but you can play changing, for example, the end time of the co-simulation, or you can, for example, choose other values for the step sizes. For example, in this one, you can choose different. different values, so 0.1 for example, and you can try with different step sizes and see that when it diverges, the error rises to very high values. Okay, this concludes part 3. If you have questions about this part, yes.
Regarding your co-simulation, you
Yes.
are running your 3 co-simulation at the same time, in
Yes.
parallel?
3 co-simulation. No, in this case, I was running first one co-simulation, then another one, then another one, then another one, from the command line. In the application, there is an option to run many co-simulations with different parameters at the same time on multiple threads.
It's also possible.
Yes, yes.
Another question?
Yes, how can one estimate the error or define a good step size without having a baseline model? So for example, in a big complex system, I have only the decoupled FMUs and not that bigger general one, how to get to a good step size?
So that's a very interesting question. Claudio, you can answer, yes.
What you do is you compare, just like what you did, you run once a really detailed co-simulation, and you use that as as you say, this is going to be my baseline.
Like alright.
Yeah.
Yeah. Alright.
And then you see how it evolves. So if you create that plot, the convergence plot between error and step size, you see where you're on the curve. And by the way, your question about determining this offline, what the order tells you the shape of this convergence function. It doesn't tell you the exact values. So it just tells you if you've got a order of accuracy of the third power, then it means that that curve will be sharply towards the origin, which indicates you are going to nicely, quickly find a good step size that's large enough. But if the order is linear, then it's going to be a painful process.
Then you have to run your detailed simulation one time. You have to accept this fact.
Yeah, yeah.
You can
In general,
also do it the other way around. You start with let's say a guess, and then you, for example, half this communication types and see if something changes.
Yeah.
If it's not changing, it should be converged.
Yeah,
right?
exactly.
Yeah.
That's the thumb rule. Yeah.
Okay. Because some of our teams are using many FMUs together, but it takes a very long time.
Yeah.
So we are trying to find another way to reduce the time and to maintain the accuracy acceptable. But
that's when you use maybe strong conflict techniques, or you improve
the platform is seen.
Yeah, we should discuss later.
Okay.
Maybe there's.
Yeah, I'm just asking for curiosity, but there's nothing like an adaptive co-simulation who maybe guesses the co-simulation errors.
For sure there is. So this is the freedom for master algorithms. So you can have more advanced things like error control in simulation. In the solver itself, you can have error control in co-simulation. So this is freedom, and there are people who have done their PhD in this direction and so on. So there's a bunch of things. Well, let's say the fixed time step co-simulation, that's the simplest thing that you can do, and there's lots of advanced stuff. And there are tools that provide advanced methods there.
And the FMI standard, can it also give some error? So it cannot give back some error of the individual.
No, that you have to do outside of.
There is the return early function, which when an FMU internally,
let's say the FMU could.
It can return earlier to say the error is too large.
Or in case of events, for example, but it's more about the master, the co-simulation algorithm around it.
Yes. So I assume there are some commercial tools that have more complex or simpler versions of this. So is that it's kind of up to us to find what works? Is it?
Yeah, there is.
Yeah.
The IntoCPS app has very basic control adaptive algorithms, and there are tools that do much better jobs. Yeah.
And if you want to reduce the physical time for simulation, only you have the option to add more potential.
Come again?
If you want to reduce the physical time.
Yeah.
I think in the mixed simulate with real-time device.
Yeah.
The only way is to add more power to the CPU.
Yeah, or use one of these adaptive schemes. Then they can take large step sizes and slow down on critical parts of the simulation. Typically, if they're changing a lot, like in the beginning of the simulation, when it's steeply changing, they take smaller steps and then it stabilizes, and they take larger steps.
But for real time, you would typically go for a fixed step, yeah?
Yeah, predictable.
Yeah.
Yeah.
That's predictable.
And you can also, if possible, you can also run a distributed co-simulation. So if the problem is that your system is very complex, you can then break in subsystems, and any subsystem composed of one or more FMUs, you can run them in a distributed environment, so that you might increase a little bit the communication delay between the FMUs, but then you might solve the problem of your power of your computer.
Yes,
because you are adding more computer.
Adding more physical.
Yes.
So we are running a little bit out of time.
We need to go.
So the coffee break will start soon. We would have perhaps 5 minutes of an outlook that
Do you want to give everything?
Claudia would present, and then I would suggest that we do a last round of questions.
Yeah, so yeah, this is more of an outlook. We have 2 parts. The first part is a list of slides that we leave here for your reference. You can consult these and see examples of different applications where FMI was used, where we detailed what was the role of FMI in this particular initial example. You can see in the slides the role of FMI was to enable the easy validation of a Gram-C on a simulated architecture. Sorry, I'm not going to go into the details, and I'm sorry, Maurizio, I'm butchering his slide on the applications where they worked very hard in the University of Pisa to enable this. We have an application on quadcopters as well, where we have used FMI. Again, I leave it for reference. Another application where we have in the medical domain, where we have used FMI. Application in platooning, platooning control, and there are other applications. Maritime, if I can see my screen. Yeah, maritime domain on the right, civil engineering at the bottom, and energy systems on the left. These are just some selected applications. There are dozens of them. Now, FMI and digital twins, a bit of a buzzword, so let's define what we mean by digital twin. When we did our research, we realized the novelty, the concept of digital twin beyond being a model or being a simulation is in seeing a digital twin as a software system that provides services for different services that are useful in connection with a real physical twin, with a real cyber-physical system. Typically, from our industrial collaborations, the physical system exists before the digital twin comes into the picture. They have a physical system in place, they've got lots of data, now they want to build a digital twin. So what is the role of FMI in this process? On the right you see the typical services we have for digital twins: visualization, monitoring, predictive maintenance, fault diagnosis, support for decision making. They want to run simulations on historical data and determine different outcomes, and then also optimization, reconfiguration of the physical twin when the environment changes. So these are the core digital twin services we've seen in our collaborations with industry. So basically the role, what is the role of FMI in each of these as an enabler of these services? First, the big opportunity that FMI brings is the possibility to bring those design time models to the deployment time. So we want companies to take their models and deploy them in a digital twin. And so, of course, FMI is a great way to implement those digital twin services without depending on tools, because many of these digital twin services use models, and that means FMI is the preferred format to import those models into your digital twins. I've got rushed through a few examples here of how models are used in each service. So, for example, for monitoring, you may employ a model to perform state estimation. So actually in previous editions of the Modelica conference there were papers describing how to do state estimation using FMI. So you can take an FMU, do state estimation with it. Why is this important for monitoring? Well, because you may want to visualize variables that cannot be measured directly from your process. Thanks to the state estimation you can do that. Or you can also detect anomalies, because by comparing the state estimators and the real data, you can detect discrepancies which will indicate something changed in the physical twin compared to your models. So this is two activities that are relevant in monitoring. You can do predictive maintenance in order to typically generate lots of data to train AI to detect trends, degradation trends on your components. The same way you can use models, therefore FMUs, to identify, to try and do fault diagnosis, because you can vary the parameters on these models to try and find a match between the model behavior and some faulty historical data. Hopefully the concrete valuation of parameters you have found will be will reflect what happened in the physical system if you have a good enough model. Support for decision making, this is a very easy one because it allows you to run, we demonstrated with FMPI, where you can run particular CSV files through your FMUs and see the behavior. This is in these digital twins, you can run simulations on historical data. And many other examples. Most of these are, really the sky is the limit in terms of how you can use models in digital twins, and that means FMI plays a fundamental role as a way to enable these applications. That's about it. Thank you very much. We have a Q&A now in the coffee.
Yeah, so thank you very much. Perhaps, is there any feedback from your side or last questions that you won't take individually to us? Any comments? We did this the first time, this tutorial. Any last comments or questions from your side? Then you are free to go into coffee break or approach us if you have individual questions.